Here's a picture. Switching to a little bit of a different technology here for a minute, just to get a better sense of that idea of here's the particle moving in, whatever object it is, moving in, coming out, and at any point in the trajectory, it's at x of t comma y of t, it's going to have a velocity vector that indicates its direction of motion and speed, and that's the velocity vector. And the claim is that if I draw a right triangle here, then this component here is just how fast it's moving in y, and this is just how fast it's moving in x. And so this velocity vector, its components are dx dt, dy dt. That's super powerful for so many things. Velocity is such an important quantity physically. And in particular, the speed is just how long that thing is. And this is the Pythagoras calculation I was alluding to earlier. It's just the square root of dx dt squared plus dy dt squared. Okay, so now I want to talk about the next step, which is suppose I wanted to know how long was going from this point to this self-intersection. And so the length, I'd like to get the length, or what you call the arc length of the curve, to emphasize that it's a curving length along some sort of arc of the curve. And the simplest kind of case is we're going to specify from a certain parameter value, from a certain time value, to another one. In a more complicated case, I might say from some xy point to another xy point, and you'd have to figure out what the t's are. Fairly standard. Okay, an extra little step that you do a lot with parametric curves. Okay, and the great thing here is that it's basically just a fairly simple elaboration of distance equals rate times time. And of course, we've seen elaborations of that in calculus. Well, let me use the word speed here, because that's usually what's used here. I've got a weird alarm going on here. Okay. Distance equals speed times time. Well, we know that's not quite true. That's the version before calculus that had constant speed. Okay. But we know how to make that better. We know that the distance, or really the length of the curve, how far you've gone along the curve, should be the integral of speed times dt from t equals a to t equals b. Let's say this is a to b in general. And think about it. Think about if I had just had these last two lines and I wasn't in the context. Ooh, I know this is not working too well with being cut off on the video. If I just had these last two lines, this could have been way back in chapter 5 when we were first doing integrals. And we talked about how you take the speed at a particular time times a little bit, run the clock a little bit. That gives you how far you've gone along the curve or in your path, and then you add them up. So it should be pretty plausible. Let me make it a little bit more official. I'm not going to prove it super carefully. By looking at this picture, let me just redo the picture and maybe make it a little bit more generic. What does this do? If I let the clock run from like some time t0 just a little bit later to t0 plus dt, that I want to figure out how far that little segment is. And if I can figure out what the length of that little segment and the next one and the next one and the next one and the next one and the next one, etc., I'm just going to add those all up. That sounds like an integral. Okay, so the length of this little bit is definitely going to be how fast am I going times how long did I let the clock run. And then you add them all up. So there's more fancy and more official derivations of this, but they all come back to this idea of segment the curve up into a bunch of little pieces, very much like a Riemann sum, but kind of a twisty Riemann sum. Look at each piece and see what happens on each piece, and then add them up with an integral. So that's all the justification I'm going to give. You can look in the book for more official ones. But really, if you understand it as the calculus version of distance equals rate times time, then we're good. Okay, so let me go back to the official, sort of the pretty printing stuff. That's probably going to be Okay, so this is where the fact that the speed simplified is going to be really nice. Okay, so the arc length, the official formula, is L. It's always from whatever your starting value is. I mean, I'm putting t equals to be emphatic about that it's the t variable that we're doing, but you don't usually need that. And then it's the speed, which is usually denoted magnitude of the velocity vector. Now, not all books, including Stewart, talk about the velocity vector first and then the speed, but I really like doing that. But the punchline, even if you haven't heard of the velocity vector, is that I'm just going to put in that formula. That's the x velocity squared plus the y velocity squared square root. Okay, you just want to think of that as Pythagoras, magnitude of a vector, length of an arrow, and that is the speed, and speed times time is distance, and I add up all the little bits of distance. So in this case, we've got a very nice fact that when we took the speed, it looked like a pretty messy thing. And honestly, if it hadn't simplified, this would be a really messy thing to put inside an integral. It'd be like a fourth power of t inside a square root, then integrate it. We don't really have tools for that. But because I chose the constants right, we got actually that it simplified to be 3 plus 3t squared. That was really nice. And the one particular example I want to do is that 1/2 of one loop, which was t equals 0 to t equals root 3. And 3 plus, I just forgot it, 3 plus 3t squared. Yeah, I just want to make sure I get it right. 3 plus 3t squared dt. Oh, that's easy. Okay. That is equal to 3t plus t cubed from 0 to root 3. And that's 3 root 3 plus, root 3 cubed, is also 3 root 3. Oh, nice. And so that's 6 root 3. So in this case, the key step was from this master formula for length to this particular result. In this case, it was really doable. You'll see a lot of problems in textbooks that say, or on the AP probably, I think, where you set this, they'll ask you to set this integral up and then either don't evaluate it or evaluate it numerically, because you just won't be able to do it algebraically. But we have tools for that. We have all kinds of numerical integration techniques and routines for that. Okay, so that's the very quick example of the story of arc length. And let me separate out area as one more separate video.